is our day 2 of rational function. Once again, 3.6. For number 1 to 3, describe the end behavior model using one of the following. Now, for A, I have y equals is 0. In other words, what will happen as x approaches plus or minus infinity? Well, if you give plus or minus infinity to x, x is not even there. It means that f of x or y will also approach 0 because there's no x. No matter what value it takes, it will be 0. For y equals k not equal to 0, this time I will say as x approaches, let's say, plus or minus infinity, f of x will approach, this time, k, not 0. Now, what will happen if you have a linear function y equals x? With a linear function, as x approaches infinity, if you put x, you make x a big positive number, y will also approach infinity. But if x approaches negative infinity, y will also approach negative infinity. For polynomials function of degree greater or equal than 2, I would say as x approaches positive or negative infinity, f of x will just approach infinity. You're probably wondering what I mean by all these data. Let's start with number 1. We have 3x cubed plus 2x squared minus x plus 7 over 5x squared minus 3. If you decide, obviously the power on top is greater than the power of the bottom, so we will have a slant asymptote. Now, if you divide these two, you will end up with something like y equals x. It might have other values, but it's going to be on the form y equals x plus something, plus 5, plus 9. It doesn't really matter what is plus, because you dropping one power. After dividing a cube by a square, you're going to have an x. It can be 5x, it can be 6x, but bottom line is going to be a positive x. So I will say as x approaches infinity, it seems like it's going to follow C. I'll mark a big C here. It's going to follow the same thing as C. So as x approaches infinity, I will say that f of x will approach infinity as well. And as x approaches negative infinity, f of x will also approach negative infinity. Let's look at number 2. Number 2, I have g of x is equal to 3x squared over 7x squared, 3x squared plus 5x minus 1 over 7x squared. Here, the coefficient on top and the bottom are the same. So my horizontal asymptote will be y equals the coefficient gain, which is 3 over 7. The fact that it looks like this, it drives me to B. It looks very similar to B. Now, let's go ahead and study as x, for B, as x approaches positive or negative infinity, plus or minus infinity, f of x will approach the same value, which is 3 over 7. Whether x approaches positive infinity or negative infinity, f of x will be at 3 over 7. The last one, I have x squared minus 2 plus x plus 3 over x squared plus 4. Obviously, this seems like it was divided already. So my slant asymptote on this one will be y equals x squared. So let me make a purple. Y equals x squared seems to be, it can be plus or minus something, but y equals x squared is the parent function of my slant asymptote. So it's following D instead. And for D, I know that as x approaches infinity, I know that f of x will also approach infinity. And as x approaches negative infinity, f of x will also go to the same infinity. Alright, for number 4 through 6, sketch a rough graph using intercept and end behavior models. First of all, I have a square on top. With a square on top, it means that it's going to bounce. So it has been factored already. As a root, if I'm looking for the roots, I have two roots. One of them at x equals -3 and also at x equals 3. But the fact that I have a perfect square at 3, it means that it's going to bounce. I have q vertical asymptote. My VA will be at x equals 5 and at x equal -4. Let's talk about our x-intercept. The x-intercept will be, in case I decide to put 0 for y, my x-intercept will be at -3, 0, and also at 3, 0. My y-intercept, the y-intercept on this one will be at 0, comma, in case I decide to cross all the x's. On top, I will have 9. 9 times 3 will be 27 over, and on the bottom, I will have 5, -20. Alright, let's go ahead and give a rough graph. Start with my x and y coordinates. The first few points I will plug in are my asymptotes. So let's start by graphing out vertical asymptote at 5. I assume this is 5. I also have a vertical asymptote at -4, somewhere here. Do I have a horizontal asymptote? Well, the power on top is bigger than the power on the bottom, so I do have a slant asymptote. And if you calculate your slant asymptote, I assume everyone knows how to calculate the slant asymptote, you will end up with y equal x minus 2. Once you calculate your slant asymptote, how do you calculate it? You will expand this, multiply by this, and divide, do your synthetic. But I have y equal x minus 2. So let me go ahead and graph also my slant asymptote. Slant asymptote would be go through -2. Keep in mind, this is just a rough graph. I'm not being very accurate, but I assume it goes through -2 here. Alright, from here, I know that it will bounce at -3. So at +3, I'll plug in the point +3, which is somewhere here. I will also plug in the point -3, which is somewhere here. My y-intercept, we said the y-intercept was at 0, -27, so it's barely here. And to graph this, I know that I will have something like this. It will cross at this point, go through this, but it will not cross here. It will go back down. In here, since I don't have any other intercept, it will do this, and also here it will do this. That's a rough graph. Note that it goes through my y-intercept here. Alright, let's go ahead and look at the second one. I'll go a little faster on this one. Well, the x-intercept is at -2, 0, and also at 5, 0. The y-intercept, I might not be going in order, but the information remain. The y-intercept, actually we have no y-intercept. Okay, the VA, the vertical asymptote is at x equals 0, x equal -3, and also x equal 4. The horizontal asymptote, here the power is 3, here the power is 4, so it's at y equals 0. So let's go ahead and graph it. I'll do a very rough graph here. At 0, I have an asymptote. So 0 is actually an asymptote. I'll make it dotted. This is an asymptote. I also have at -3. I also have at +4. Now, do I have any at y equals 0 is also an asymptote. So all these are asymptotes so far. Now, my x-intercept is at -2 and at 5. -2 is somewhere here, and 5 is actually past here because this is at 4. So 5 is here, and this is 0. From here, I know that the perfect square on the bottom tells me they come together. So they will come together at x equal 4. So at x equal 4, they will come together. Now, since there's no, they can either come together here or here. How will I know which way? You can plug in a value if needed, if you want to double check where it goes. But on this side, I also know that at x plus 2, it will bounce. So I know that at this level, it will bounce. It will be a u up or down. And I know that on the back side, let's go ahead and plug in. I'll plug in a huge, I want to know, I'll use this information actually. I know that I have y equals 0. So as x approach plus or minus infinity, f of x will approach 0. So it will approach 0 on both sides. So it will come closer to this axis. The next thing I will do is this then. I will graph it like this. It gets closer, but it doesn't touch. I also know that it will bounce at -2. In here, it will go like this probably, because they have to come together at 5. Now, although it crosses here, this is a vertical asymptote, so it will come back in line close to this. Let's look at number 6 now. Number 6 is started with a negative. The leading coefficient is negative. The fact that the leading coefficient is negative, actually, let's not talk about it. Let's just do x-intercept first. I have x-intercept. I have y-intercept. I will need to find if we have any dA. 1, 2, 3. The power on top is greater, so I have a slant asymptote on this one. Alright, for the x-intercept, I have it at 2, 0. I have it at -3, 0. And I also have it at 5, 0. For y-intercept, if I cross all the x's, you will end up with 0, negative 2 times 3, 6, 5 times 6, 30 over 5. 30 over 5. So it will be 15 over 2. Let's cross it. For my y-intercept, I get 30 over 4, meaning 15 over 2 with a negative. Vertical asymptote, I have x equal 1 and also x equals 4. Slant asymptote is that y equals, once again, if you compute it, you will get negative x minus 1. My goal is to show us a rough graph. Alright, let's go ahead and graph our axes. X and y axis. Slant asymptote is now negative x minus 1. So I'm graphing my slant asymptote somewhere here. I have at x equal 1, I have an asymptote, so I have 1 here. I also have an asymptote at x equal 4, meaning here. I'm not being very accurate, but you get the idea. I have a y-intercept at 0, negative 15 over 2, so it's somewhere down here. I have an x-intercept at 2, 0. I will have also a negative 3, 0. 2, 0 is somewhere in between here. And I also have another one at 5, meaning here. Obviously, the graph will look like this. It will come like this, cross here, cross also here, and get low. In between here, I don't have any perfect square. The fact that I don't have a perfect square, it means it will cross here. You're probably wondering why is it crossing the slant asymptote, but yes, that's possible. And the last one will come like this and probably have this as a slant. An asymptote is the behavior of the graph at x approaches infinity. So for the slant, the behavior is still not touching, but in between it doesn't really matter. All right, answer the question about a rational function f of x. Describe the following statement. I have a less or equal to 0 and 0 less than b less than c. So I have all these. I'll let y'all read this. List all vertical asymptote. Vertical asymptote will be at x equal a and at x equal c. That will be your vertical asymptote. List all holes. The holes will be at b, f of b. And what is f of b? F of b here is 2. F of c, be as specific as possible. Well, we can't find f of c because if x is equal to c is a vertical asymptote, f of c is not defined. So this is not defined. All right, what is the degree of the denominator of f of x? The degree of the denominator, if we have 1, 2 plus this, by the way, this would be a whole, that would be 3. Meaning we have 1 vertical, 2 vertical, and the whole. The degree must be 3. The degree of the numerator of f of x. Well, the degree of the numerator must be 4. Sketch a graph of f of x. Let's go ahead and try to sketch something here. I will have an x-axis. Not this, but x-axis, y-axis. We know we have asymptotes. We have couple asymptotes. One of them at x equals a, and the other one is at x equals c. I can graph a here, why not c here. And we have a slant asymptote. I'll graph a slant asymptote. We know that this value is a. I'm calling this one a. I'm calling this one b. And this is my slant asymptote. Actually, this is c. B is the whole, so we need a whole somewhere. And f of b is 2. So if this is 2, and this is b, this is f of b. I put a hole there. And I know that the graph will do something like this. Go through the hole, come back down, and it will be here and here. By the way, it goes straight down. Not, it doesn't curve like that one I did. Last portion says, write an equation of f of x using the condition 1 through 5 above. Now, f of x is equal to, we know that on the bottom we will have x minus a, x minus b, and x minus c. In order for b to be a whole, I must have x minus b also on top. Nothing bounds, no square. And on top I will have x minus a constant, I can call it k, and the degree on top is 4, so I'll put 3 here because this is 3 plus 1, 4. I forgot one more thing. What is k? The constant is this value here. K will be your x-intercept.